This video lecture is meant to cover the information found in Unit 9.2 on potential energy diagrams. Potential energy diagrams are a way to visualize endothermic and exothermic reactions, and it also shows you a little bit of something about activation energy. We're going to take a look at first endothermic reactions. If you're shown a chemical equation and the energy term is on the left side of the equation, you know it is exothermic. Alternatively, you also know it's exothermic if the delta H, or the enthalpy change, is positive. These values can be found on Table I of your reference tables. You can also, what this means for a reaction to be endothermic, it means that energy is absorbed by the reactants. All right, what this looks like on a potential energy diagram. First of all, you'll have potential energy on the y-axis, and you will have what is called the reaction coordinate on the x-axis. Reaction coordinate is really just showing that the progress of the reaction over time is going in that direction. There's basically this shape to an endothermic reaction. The first plateau is the potential energy of the reactants. The second plateau is the energy of the products. And let's see, what else can we label here? If we made a line here at this first plateau and at the second plateau, that difference right there is what we call the delta H. That is the enthalpy change. Alternatively, sometimes you will see it extended out this way. So the difference between the potential energy of the products and the potential energy of the reactants is called delta H, which is, of course, enthalpy, or the heat of the reaction. In this case, it is positive because you're starting at a lower energy and you're going to a higher potential energy, so that is a positive enthalpy change. We can determine the activation energy. The activation energy is starting from the potential energy of the reactants, this line right here, going all the way up to the peak of the curve. This is known as the activation energy. The other thing that you might possibly be asked to do is to show the catalyzed reaction. So if I use a different color pen here, you might see a catalyzed reaction where the activation energy is lowered. Okay, so the hump is still has to go above where the products will end up as, but it'll be a lower hump and it'll get to the product potential energy sooner. So that right there is the catalyzed reaction. All right, so let's take a look at we'll push this up a little bit and we'll take a look at exothermic reactions. Okay, for exothermic reactions, the energy term is on the right side of the chemical equations. The energy term on the right side of the equation. You will also notice that the delta H's will be negative on Table I. And what this means is that energy is released. So if we were to look at a potential energy diagram for an exothermic equation, we have potential energy on the y-axis and the reaction coordinate on the right side. We'd see the reactant's energy is higher than the product's potential energy. If we read over here to this line, that's your delta H. Okay, you might also see it inside the graph like that. That's your delta H, that's your enthalpy change. The activation energy would be from wherever the reactants start up to the peak. So that is your activation energy. Now you may be asked to read these. Oh, and of course, if we were to catalyze this, same idea is that the peak would be lower and you would reach your product's enthalpy a little bit sooner. So that would be the catalyzed reaction. Now the only other thing that you might be asked to do is to, if you're given the activation energy of the forward reaction and the activation of the reverse reaction, you have to be able to read this in reverse. So if this reaction were going in this direction, this now becomes your reactants and these become your products. and your activation energy would be from this line all the way up to this line right here. So the difference in the activation energy of the forward reaction and the activation energy of the reverse reaction is going to end up being your delta H. Kind of an interesting way to look at it. All right, let's take a look at our practice problems. We are looking at question number 7. Which diagram has the lowest energy of activation? So you're looking wherever the reactants start, right here, up to the peak, where the reactants start, up to the peak, where the reactants start, up to the peak, where the reactants start, up to the peak. So it looks like that choice D has the lowest energy of activation. Number 8, how does a catalyst alter the shape of a potential energy diagram for a reaction? Does it require additional activation energy peak? Does it lower the original activation energy peak? Does it raise the does it raise the original activation energy peak, or it lowers the energy of the products? Okay, so the products energy and the reactants energy will never change. It is that activation energy peak that will get lowered. So it's got to be choice B right there. An energy diagram, number 9, shows the forward activation energy is 40 kJs per mole, and the reverse activation energy is 20 kJs per mole. What is the value of delta H of the reaction? So here, if you wanted to sketch this to see this visually, all right, so the forward activation energy is 40, but the reverse is 20. That tells me that this is an endothermic reaction, because the forward reaction energy here, this is 40, and then here, the reverse reaction, if we're going from right to left, that right there is 20, right? So that means the difference between the products and the reactants has to be 20 right there. And it would have to be a positive 20 because the products end up at a higher energy level than the reactants. It is endothermic, so it is positive 20 right there. All right, I believe that is it for section 2 on potential energy diagrams.